Hello again. We are almost at the end. We have this section and one more from chapter 11, and that's the end of the course. Hello again. This time we're going to talk about Taylor and Maclaurin series. Maclaurin series is a special case of the Taylor series when x is 0. Actually, when a is 0, sorry. So we look at more general functions and which functions have power series representations and how we find such a representation for a function. A representation of a function of a power series and vice versa. If we have a power series representation, can we determine the function that it belongs to? Okay, so the Taylor series of a function f of x at a, or centered at a, is this series. So f of x is the sum from n equals 0 to infinity. This is the nth derivative of the function evaluated at a, x minus a to the nth power over n factorial. And as I was mentioning, this is the Taylor series. The Maclaurin series is exactly the same, but when a is 0. So then we have the nth derivative of the function evaluated at 0 divided by n factorial, x minus 0, which is x to the nth power. And this is the Maclaurin series representation of f of x. This is a Taylor series representation of f of x. And of course, the radius of convergence is r. Note, there is no guarantee that the sum of the series equals the function. There is no guarantee that the sum of these series equals the function. The same thing here. And we have some facts that I would like you to add to table 1. So a lot of what we're doing in this section evolves around table 1 on page 804. Okay, it's also in the Canvas course. I copied it there for you. So we have 3 pieces of information that I would like to re-emphasize here. The limit of x to the end of n factorial is 0 when n approaches infinity. The series representation of E is this, the sum from n equals 0 to infinity from 1 over n factorial. And this is also mentioned in table 1 on page 804. So the series representation for e to the x, and this is true for all x because the radius of convergence is everything. Okay, so I think we're going next to look at some problems, and we start on page 808 with problem 3. Okay, and it says, given the nth derivative of a function at 0 is n plus 1 factorial for n equals 0, 1, 2, and so on and so forth, find the Maclaurin series for f and its radius of convergence. So we know that the definition is f of x equals the sum from n equals 0 to infinity from f differentiated nth times at 0 n factorial and x to the nth power. And this is the Maclaurin series for f of x. We are given this piece. As you see, the nth derivative at 0 is n plus 1 factorial. So what we're going to do is just replace it and see what happens. So the sum from n equals 0 to infinity, n plus 1 factorial over n factorial x to the nth power. And now let's see. Well, if you remember, n plus 1 factorial can be rewritten as n plus 1 times n factorial over n factorial, and we will simplify these two. N factorial with n factorial. So the representation will be, or the Maclaurin series will be n plus 1 x to the nth power. Now the problem is also asking us to find the radius of convergence. So we're going to use the ratio test for that, and we will determine the limit as n approaches infinity. As you know, from n plus first, so this is n plus 2 x to n plus first over n plus 1 x to the nth power. this limit approaches 1. Let's see what we have left here, and that's basically the absolute value of x, which is has to be less than 1 by the ratio test for the series to converge. So then the radius of convergence is 1. Okay, let's move on to another one similar to this, number 4 on 808. But this time the question is, find the Taylor series, not the Maclaurin series, but find the Taylor series for f centered at a equals 4. And they're giving us the nth derivative at 4 of the function at 4 as being -1 to the nth power, n factorial, 3 to the nth power times n plus 1. So now we're going to write the Taylor series, and let's see what we need to do next. So that's my page 3. Okay, perfect. So f of x, the sum, n equals 0 to infinity, the nth derivative evaluated at a divided by n factorial, and x minus a to the nth power. This is the Taylor. So let me write here, maybe I should write Maclaurin. Okay, and here maybe I should write Taylor, so we know. Okay, perfect. So in our case, a equals 4. So the function will be represented as f of x equals the sum from n equals 0 to infinity. The nth derivative has to be in parentheses, so the nth derivative at 4 over n factorial x minus 4 to the nth power. We are given this piece. We have it. So I'm going to replace it. So the sum equals 0 to infinity. And we have -1 to the nth power n factorial over n factorial 3 to the n plus 1. So I replaced all this. I copied n factorial, and now x minus 4 to the nth power. Okay, of course these two go away. So what is left is the sum from n equals 0 to infinity. -1 to the nth power, x minus 4 to the nth power over, of course, it should have been a little bit higher, sorry about that. So the sum, the fraction line has to be in the middle of the sigma or summation notation, not below it. Just to make sure that that's clear. So over 3 to the nth, n plus 1. Okay, so we are also asked to find the radius of convergence. So let's find the radius of convergence with the same ratio test. So the limit as n approaches infinity, all this to n plus 1, x minus 4 to n plus 1, over 3 to n plus 1 and n plus 2. When n is n plus 1, we have n plus 2 times 3 to the n plus 1 over -1 to the nth power, x minus 4 to the nth power. Okay, so let's see what goes away, and let's find this limit. Okay. So 3 to the n will go away with 3 to the n, but there is still a 3 left in there. X minus 4 to the nth power with x minus 4 to n plus 4, so there is an x minus 4 left in there. This limit will approach 1, or this limit is 1 when we determine this limit of n plus 1 over n plus 2. A -1 to n plus 1 over -1 to the n, they will go away because of the absolute value. So what is left, that's my page 4, what is left is the absolute value of x minus 4 divided by 3. By the ratio test, for this to be convergent, for the series to be convergent, it has to be less than 1, which really translates into this, or the radius of convergence 3. Okay, let's move on to a different type of problem. 11 on 808. Find the Maclaurin series for f of x using the definition of Maclaurin series. Fine. And we are given the function. And find the radius of convergence. So the function in 11 is f of x equals 1 minus x to negative 2. Okay. So for the Maclaurin series, let's write it again. So this is f of x, the sum from n equals 0 to infinity, the nth derivative of this function evaluated at 0 over n factorial times x minus a, but a is 0, x to the nth power. So this is the Maclaurin series. All we need to determine is this piece. This is what we do not have. In order to determine that, I have to analyze this function and find its derivatives till the nth one. So let's start slowly with the function, which is this. I'm going to copy it again. So f of x equals 1 minus x to negative 2. And let's find the first derivative. Bring down negative 2. Subtract 1 from the power times the inner function prime, which is negative 1. The second derivative, we have negative 6, 1 minus x to negative 4 times the inner function prime, which is negative 1. The third derivative, negative 24, 1 minus x to negative 5 times the inner function prime. And now let's see if we can come up with the nth derivative of this function. So when we differentiate the first time, the power is negative 3. So when n equals 1, the power is negative 3. When n equals 2, the power is negative 4. When n equals 3, the power is negative 5. So obviously I see the pattern here. So we are looking at negative n plus 2. When n is 1, 1 plus 2 is 3, minus 3. When n is 2, 2 plus 2 is 4, negative 4. When n is 3, and so on and so forth. So this is clear now, which is the power of 1 minus x. Fine. But what do I do with 1, 2, 6, 24? So please remember, these are factorials. So 1, 2, 6, 24. This will be 1 factorial, 2 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on and so forth. So 1 has 2 factorial. 2 has 3 factorial. 3 has 4 factorial. So obviously we are looking at n plus first factorial. Then we have the 1 minus x, and as we discussed, the power is negative n plus 2 in parentheses. We can stop for a moment and check again. For the first derivative, we have 2. 2 factorial is 2. 2 plus 2 is 4. For the first one, sorry. 1. 1 plus 1 is 2. So 1 plus 2 is 3, negative 3. Correct. For the second derivative, 2 plus 1 is 3. 3 factorial is indeed 6. 2 plus 2, that's correct. So this is this piece. So now we're ready to write the function as a power series. Let me do this. So although I see it, I have it, so it's okay. Okay, that's my page 5. So then we have f of x equals the sum from n equals 0 to infinity. This n plus 1 factorial 1 minus x to negative n plus 2. Everything divided by n factorial and everything times x to the nth power. So now let's see what we can simplify from here. Okay. So again, this piece will be written as n plus 1 times n factorial. So let's do that. N plus 1 times n factorial. And here we have the Maclaurin series. Oh, I forgot. So sorry about that. When x is 0, 1 to negative n plus 2 is going to be 1. Okay, so n factorial times x to the n factorial over n factorial, because we were asked to use Maclaurin series. So for Maclaurin series, we need to determine f, the nth derivative of f at 0. So I had to replace x by 0. Okay. So this is okay, but now we are replacing x by 0. Just here, actually, right? Not here. Good. So we simplify. So n equals 0 to infinity, n plus 1, x to the nth power. Okay. So now all we need to do is find the radius of convergence. Again, with the ratio test. So we have n plus 2 to x to n plus first, n plus 1 x to n. This limit will go to 1. X to the n plus first over x to the n is x, less than 1. So the radius of convergence is 1. Okay. Moving on to 23. Let's see how we are on time. Still good. Okay, 23. On the same page. Yes, 808. Find the Taylor series centered at the given value of a. So here we are given f of x, which is natural log x, and they're telling us that a equals 2. Good. So let's see. We're talking about the Taylor series, of course. Again, we can write it as f of x, sum n equals 0 to infinity, the nth derivative at 2 over n factorial, x minus 2 to the nth power. Good. Again, we have to discover this in order to continue. So in order to find that, the nth derivative at 2, again, we have to look at a bunch of them. So let's start. So f of x equals natural log x. F prime of x equals 1 over x, or x to negative 1 for convenience. The second derivative will be negative x to negative 2. The third derivative will be 2x to negative 3. The fourth derivative will be negative 6x to negative 4. And now we need to discover the nth derivative and then plug in 2 in it before I put it here. So let's see what we conclude about this. First of all, there is a negative 1 in front. So this is positive, this is negative, this is positive, and this is negative. So there must be a negative 1. And let's see which power. N plus first, let's see. When n is 1, then this is positive. When n is 2, then this is negative. When n is 3, then this is positive because 3 plus 1 is 4, and so on and so on. That's good. Now let's see what we have in front. First derivative, 1. Second derivative, 1. Third derivative, 2. So this is 2 factorial, but n is 3. This is 3 factorial, but n is 4. So we are looking at n minus 1 factorial. Okay, and then first negative 1, second negative 2, third negative 3. So times x to negative n. Of course, I ran out of room. I'm going to write it again. So let me copy it here so everyone can see it. So the nth derivative would be negative 1 to n plus first times n minus 1 factorial times x to negative n. But now we have to find the value of this derivative at 2. So all I have to do is write 2 to negative n. Everything else stays. So then I do have this piece of the coefficient. These are the coefficients, but this, I have this piece. So now we are ready to write the whole thing. So then f of x, which is natural log x, is the same with the sum n equals 0 to infinity. I have to copy this and divide by n factorial. Negative 1 to n plus 1, n minus 1 factorial, 2 to negative n, everything divided by n factorial, and multiplied by x minus 2 to the nth power. Now we have to clean it up a little bit and find the radius of convergence. That's all we needed to do. Okay, so let's see how we clean it up a little bit. So I will replace this by n times n minus 1 factorial, so I can simplify these two. So the sum, n equals 0 to infinity, negative 1 to n plus first, times x minus 2 to the nth power. There is still an n, and 2 to the n. So n, 2 to the n power, because it was negative here, it goes to the denominator as positive. So negative 1 to n plus 1, x minus 2 to the nth power over n times 2 to the nth power. So this is the power series representation. It's a Taylor series representation of natural log at a equals 2. The Taylor series representation of natural log at 2. So now all we need to do is find the radius of convergence, and we can move on to the next problem. So for the radius of convergence, we will determine the limit as n approaches infinity from this, the next term, the n plus first, so negative 1 to n plus 2, x minus 2 to n plus 1, n plus 1, and times 2 to n plus first, and I flip, n 2 to the nth power, negative 1 to n plus first, and x minus 2 to the nth power. Okay, so let's see what goes away. This limit will be 1. We have a 2 left here. This will go away. It's the absolute value anyway. And from here, we have in the numerator an x minus 2. So the answer will be the absolute value of x minus 2 over 2, which by the ratio test has to be less than 1 for the series to converge. So then we have x minus 2 in absolute value less than 2, which guarantees the radius of convergence to be 2. Second half in the second video. Thank you.